Good afternoon, everyone, and welcome to our webinar on improving your thermal reliability. Before we proceed, please note that all participants are currently muted to ensure a smooth and focused presentation. However, we encourage you to actively participate and make most of the session. You can share your thoughts, questions, or comments in the chat throughout the whole webinar. So I'm Jubaida, and I'll give you an insight of thermal reliability, how thermal reliability you can be using ANSYS products to optimize your business Okay, so some of the agendas that we're going to discuss today is an introduction to thermal reliability, so understanding your thermal reliability challenges, understanding the importance of managing your thermal reliabilities, thermal reliability solution, design optimization, and reliability improvement. We're also going to look into how you could optimize your business and reduce their cost through software simulation by reducing the need of physical testing, material and manufacturing cost, and also reliability prediction and improvement. Then I'm going to invite my colleague Rob to go through some of the technical challenges and do a demo for you guys. So electronic systems are found in nearly all industries, everything from aerospace, automotive to consumer electronics and healthcare. To ensure the systems remains operational and perform their intended functions in a variety of environments, it is critical for product success and customer satisfaction. Companies who properly address electronic reliability concerns through simulation can meet many of the objectives stated here. Traditionally, companies have used a design, build, test, then break and fix in the design cycle. This process can be very expensive and time consuming. The design rules and best practice associated with this process may not provide the engineers with enough guidance to properly design modern cutting-edge products. By using simulation, virtual prototypes can be created and tested virtually. This provides engineers with higher degree of confidence that the eventual physical testing they do run will be successful. Performance, safety, and cost are critical consideration in design of electronic systems. Designs are required to reliably perform their intended functions in a wide variety of demanding environments. If electronic systems gets too hot or have any mechanical failure, they may not be able to perform their intended functions. In some cases, such as automotive, aerospace, and healthcare, this could put people's lives at risk. Many existing customers of ANSYS benefits from the reduced design development and material cost, reduced product development timeline, and improved product performance and reliability by moving from physical testing to virtual product testing. Engineers must address a wide variety of design requirements when designing electronic systems. This ranges from electrical, such as signal and power integrity, thermal, such as implementation of optimal cooling strategies, or mechanical consideration, including the ability to withstand thermal cycling, shock vibration, and drop. Additionally, products are required to meet life requirements to make sure they meet their intended functions for at least a specified amount of time. Engineers who required to consider the effect of manufacturing, transportation, and product operation as a part of their design process. ANSYS provides a range of workflow solution that addresses a wide varieties of electronic reliability concerns. Its simulation toolsets plays a key role in understanding how electronic systems operate and perform in a variety of applications. Over the next couple of weeks, we will focus on each of the areas in a separate short webinar. In our last webinar, we have discussed the electrical reliability. We discussed electronic simulation to address concerns related to signal and power integrity, EMI, and EMC. If you would be interested, you could request a recorded version of that webinar. So in thermal reliability, we're going to focus on maintaining thermal integrity as an essential part of designing best-in-class electronic systems. Thermal solutions allow engineers to evaluate and optimize cooling strategies and component designs. Using ANSYS tools, user can evaluate thermal performance from chip die level all the way up to the system data central level. User can also consider downstream effects such as thermal mechanical effects as PCB and package wrappage and stress. I'm now going to hand this presentation over to my colleague, Rob, who will be going through some of the technical element of thermal reliability using ANSYS simulation. So over to you, Rob.
Thanks, Jabida. Brilliant. Yeah, so we're going to look in this webinar on thermal reliability. I'm just going to go through some of the tools and solutions that the ANSYS electronic suite offers. And then, yeah, as Jabida says, we're going to have a closer look at some of the software. And then we're going to open up to some questions. So there's thermal reliability in electronics it's incredibly important. You got to acknowledge that all electronic devices and circuits are going to generate heat during their normal operation, and this is a natural consequence that arises from electrical flow and currents through various components that can result in resistive losses within the system. So engineered thermal management is a fundamental process in designing and manufacturing electronic devices, and its importance lies in reducing and minimizing several critical issues that can greatly impact the performance and safety of our products. So first, there's excessive heat buildup can lead to catastrophic failures within electronic components and cause irreparable damage and can compromise the safety of the device. Heat-induced performance degradation can result in operational robustness issues, affecting the overall efficiency and functionality of the system. And insufficient thermal management can shorten the product's lifespan, causing premature failures and reducing the expected operational life. So in electronics, thermal management plays a pivotal role in assessing the reliability and the robustness of electronic devices, and by utilizing advanced system techniques, advanced simulation techniques such as ANSYS simulation suite and modeling the systems, you can accurately predict and evaluate the performance, the thermal behavior of the system under varying operational conditions. Through identifying hotspots, you can optimize your cooling strategies, and you can end up validating any design choices that you've hopefully used ANSYS to design in early in the design process. Apologies. So at the ANSYS offers solutions across all the scales of electronic applications. From the chip die level, using packages like Red Hawk, to the integrated circuit level, again using Red Hawk. But at the package level, you might use Q3D or HFSS. The board assembly, where you would be looking at using SI Wave and HFSS, and sometimes Q3D, and then all the way up to backplane assembly and system level, and then all the way up to even the supercomputer or the server room / data center and an open environment where you can find dead zones in the airflow that it's used to cool, like say the data center racks. So chip thermal reliability. So as electronic devices continue to push the boundaries of performance, managing temperature-dependent chip power and mitigating electromigration issues are vital for ensuring the long-term reliability of the product. And ANSYS offers a comprehensive solution that leverages ANSYS I, which provides an accurate chip-aware system-level thermal result and system-aware chip-level thermal results. So as electronics become more sophisticated, the power dissipation within chips becomes increasingly temperature dependent, and high operating temperatures can exacerbate the risks of electromigration, which can lead to reliability issues and potential failures of the chip. The chip package system reliability workflow that ANSYS has introduced combines the power of two powerful simulation tools, IcePack and RedHawk CTA. So ANSYS IcePack is a robust thermal analysis software that is designed to model and analyze the thermal behavior of complex electronic systems. It provides chip-aware system-level thermal results, which allows engineers to understand how heat is generated by individual chips and how that impacts the overall system temperature. With IcePack, you can precisely model the thermal interaction between the chips and components and the surrounding air and your cooling solution. You can identify potential hotspots, and you can use those hotspots to optimize the cooling design to ensure a uniform temperature distribution and prevent overheating. And you can analyze the effects of different operating conditions to help make informed design choices that are going to enhance your thermal performance and system reliability. ANSYS RedHawk is a cutting-edge chip thermal. Apologies for that. It's a cutting-edge system-aware chip-level thermal that provides system-aware chip-level thermal results. It considers the impact of system-level thermal conditions on individual chips, and that enables comprehensive assessment of chip thermal reliability. With ANSYS RedHawk, you can analyze the temperature gradients and thermal cycling effects within the chip. You can predict and mitigate the risks of electromigration due to elevated chip temperatures, and you can optimize the distribution strategies and maintain chip temperature and hope to maintain the temperature of the chip within safe operating limits. You see here, this is the workflow where you integrated simulation for a thermal array using RedHawk Totem, and you can pass that chip thermal model through a system thermal simulation within IcePack, and then you can pass those temperature or heat transfer coefficients back into your integrated circuit simulation for a two-way analysis. So package thermal reliability, IcePack also offers an exceptional solution to address the challenges faced by original equipment manufacturers in accurately characterizing and estimating the thermal performance of packages in unique design configurations. By providing a high-fidelity package modeling capability, IcePack allows for the creation of detailed, compact network thermal models of IC packages. So as OEMs strive to design advanced electronic systems, accurately characterizing the thermal performance of the packages in unique configurations becomes a critical challenge. And package thermal reliability heavily influences the overall system performance and longevity, and this necessitates precise thermal analysis. So first, ANSYS IcePack enables the creation of comprehensive thermal models for the IC packages, capturing the intricate details and geometries which are crucial for accurate simulations. Compact models ensure efficient simulations without sacrificing accuracy, and network thermal models provide robust platform for analyzing complex package configurations. IcePack also supports a variety of network thermal models, including two resistor, star, and Delphi models. This versatility allows engineers to choose the most appropriate model for the specific package configuration, and which will help yield precise thermal results. IcePack also seamlessly integrates with various layout tools, facilitating the import of EDA's data for streamlined thermal modeling. And moreover, engineers can import die power maps from various tools, which will enable accurate power dissipation simulations. IcePack empowers the engineer to obtain a detailed thermal conductivity map for package substrate. This information is crucial for understanding heat dissipation patterns and optimizing thermal pathways. IcePack streamlines the simulation process by automatically creating JEDEC chambers, allowing you to simulate package thermal behavior in industry standard test conditions. And ANSYS is IcePack also seamlessly integrates with other ANSYS tools such as SI Wave, which is used for signal integrity and power integrity analysis, and Mechanical, which is used for structural analysis. This multi-physics workflow ensures a comprehensive analysis of package thermal reliability, which considers the thermal, electromagnetic, and the mechanical aspects of the system. So for PCB thermal reliability, the solution to address the challenges faced in ensuring that the PCBs are thermally reliable is a critical aspect in overall electronics reliability. The modern PCB design is becoming increasingly complex, detailed, and compact, and you need for thermal simulation is more important than ever. PCB reliability forms a bedrock of overall electronics reliability, and as modern PCB designs evolve to support advanced technologies, the complexities of thermal management become a significant challenge. Accurate thermal analysis is vital to prevent the potential failures and ensure the longevity of electronic devices. IcePack provides a comprehensive solution to address this thermal challenge. It facilitates thermal simulation for both single and rack-mounted PCBs. Whether you're dealing with individual boards or complex server racks, IcePack can deliver accurate thermal analysis. It seamlessly integrates the various board layout tools, enabling direct import of EDAs. This streamlined process saves time and ensures precise representation of PCB's geometry in the thermal model. Accurate thermal pathways, they're crucial for understanding the heat dissipation patterns within PCBs and packaged substrates. And IcePack provides local varying thermal conductivity maps, which can be calculated from trace and via data for each layer of the PCB, which captures the intricate thermal behavior. And IcePack accurately models the resistive heating of the traces within the PCB. This enables you to identify potential hotspots and make informed decisions about optimizing trace layouts and help minimize thermal issues. And again, ANSYS IcePack seamlessly integrates with other ANSYS tools. And this multi-physics workflow ensures a comprehensive analysis of the PCB thermal reliability, which again, considering thermal, electromagnetic, and mechanical aspects. So now we're going to look at some enabling features. IcePack offers a robust solution to address the challenge of thermal reliability in modern and complex electronic systems. With the increasing complexity of electronic systems, it becomes essential to integrate mechanical and electrical designs from various tools seamlessly. Design of model electronic systems poses a unique challenge due to the increasing complexity, and integrating mechanical and electrical components from different design tools demands a streamlined approach to achieve accurate, reliable thermal analysis. IcePack offers the flexibility to import both mechanical MCAD and electronic ECAD data from wide variety of formats, and this seamless integration ensures that the thermal model accurately represents a complete electronic system, taking into account both the mechanical and the electrical components. With IcePack, engineers can effortlessly integrate components, packages, PCBs, and subsystems and other elements into a comprehensive thermal model of the entire electronic system. And this holistic approach allows for accurate and detailed analysis of the thermal behavior of the entire system. And IcePack is also able to perform a comprehensive system-level thermal analysis, taking into account the interactions and thermal dependencies between different components and subsystems. This enables full understanding of how the temperature variations affect the overall performance and reliability of the electronic system. But now we'll look at some enabling features. So the dynamic and diverse workload of applications often leads to power and temperature imbalances among the different cores within electronic devices. As various tasks and processes demand varying levels of computational resources, certain cores may experience higher power dissipation, and elevated temperatures. And this phenomenon can result in increased cooling costs and reduced reliability, creating a challenge for efficient and reliable thermal management. So the solution is ANSYS Dynamic Thermal Management. ANSYS offers a powerful solution for addressing these challenges through its dynamic thermal management capabilities. And by leveraging the transient solver and robust scripting features, ANSYS enables accurate modeling of dynamic power profiles, allowing for efficient and effective thermal management. So transient solver capabilities, ANSYS utilizes a transient solver capable of accurately simulating a dynamic thermal behavior. And this solver considers the time-dependent changes in power dissipation and temperature, reflecting the real-world fluctuations in electronic devices in an electronic device's workload. Scripting, the integration of powerful scripting capabilities grants you engineers with precise control over thermal dissipation based on time, temperature, and user-defined logical constraints. This level of flexibility enables the implementation of intelligent and adaptive thermal management strategies. ANSYS Dynamic Management allows for the power throttling based on local temperatures. And by monitoring the temperatures of specific regions within a device, the system can dynamically adjust power levels to prevent overheating and ensure optimal performance. You have the freedom to define custom power profiles and temperature dependencies according to their specific application and requirements. This flexibility allows for the tailored thermal management strategies, optimizing the performance and reliability. So next, network modeling. So depending on the model scope, it may not always be necessary to include minute details when while still obtaining accurate thermal responses at key locations. ANSYS offers a powerful solution through its network modeling capabilities, allowing engineers to create fully characterized thermal networks that represent both simple and arbitrarily complex thermal systems. And this versatile approach enables the representation of a wide range of applications, from IC packages with single or multiple heat sources to external heat exchangers, liquid loop cold plates, heat pipes, and more. The challenge lies in achieving accurate thermal analysis while managing the computational complexity. In many cases, including the fine details, can be computationally intensive, leading to longer analysis times. However, obtaining accurate thermal responses at specific locations remains essential for comprehensive analysis. So the representation of simple or thermal systems with ANSYS network modeling, and you can model both simple and arbitrarily complex thermal systems with ease by abstracting the detailed geometry into network representation. Thermal analysis becomes computationally efficient without compromising accuracy. The versatility of the network modeling extends to steady state and transient thermal behavior analysis. You can choose the appropriate analysis based on the specific application and desired level of detail. And ANSYS network modeling is suitable for a variety of applications, including integrated circuit packages with single or multiple heat sources, and it can also accurately represent external heat exchangers, as I've said, like open loop systems, liquid loop cold plates, heat pipes, and many other thermal components which are commonly used in electronic cooling systems. So the success of modern electronics relies on the seamless integration of multiple physical phenomena during the design process. The ANSYS suite offers a comprehensive multi-physics solution that addresses the bidirectional electrothermal workflows for chip, package, board, and system-level designs. By establishing seamless connections with ANSYS Mechanical and ANSYS Sherlock, engineers can accurately consider thermal-mechanical interactions. Additionally, ANSYS provides best-in-class reduced-order modeling solution to further enhance the efficiency and accuracy of the design process. So the comprehensive multi-physics solution offered by ANSYS enables bi-directional electrothermal workflows that facilitate the interaction between electrical and thermal aspects of electronic designs. Engineers can seamlessly model how electrical power influences the thermal behavior and vice versa, and this helps ensure an accurate representation of the system's performance under real-world conditions. The integration with ANSYS Mechanical empowers engineers to consider thermal mechanical interactions effectively. And by combining the thermal and mechanical analysis, designers can understand how thermal stresses and deformations impact the overall structural integrity of the electronic system. And ANSYS Sherlock further enhances the design process by allowing engineers to perform accelerated life testing and reliability analysis, ensuring robust and durable product designs. ANSYS reduced order modeling solutions provide a cutting-edge approach to optimize the efficiency and accuracy of the design processes. By capturing essential aspects of the complex multiphysics behavior in simplified models, you can achieve a faster simulation without compromising on accuracy. And this is especially valuable when dealing with a large-scale system where the computational resources and time are critical. You see here, ANSYS IcePack very much is the linchpin between a lot of these comprehensive multiphysics analyses, linking electromagnetics with Red Hawk and the PCB level EM, and the structural and reliability aspect, and then overall making an overall system or reduced order model with ANSYS Twin Builder. So in conclusion for this part, thermal reliability is foundational to the overall reliability of electronic systems, and ANSYS IcePack's capability to import a detailed source data from both ECAD and MCAD is crucial in creating accurate thermal models. And by importing a wide array of formats, IcePack ensures an efficient and precise model creation, allowing engineers to represent complex geometries and components accurately. ANSYS offers a wide and advanced physics modeling at various scales, from chip package to PCB and further. These simulations provide key insights into critical aspects of thermal performance, such as temperature distribution, heat dissipation, power throttling based on temperature-dependent power profiles. And moreover, the analysis of electron migration helps identify potential reliability concerns related to the movement of metal ions due to temperature gradients and high current densities, which can be spotted early in the design process. The seamless integration with ANSYS IcePack results with an ANSYS Mechanical and ANSYS Sherlock brings significant benefits to the engineers. Understanding how thermal design affects product longevity and expected failure rates is vital in predicting and addressing potential issues before they occur. And by coupling thermal analysis with structural analysis with ANSYS Mechanical and reliability analysis with Sherlock, engineers can gain a comprehensive insight into the interaction between thermal and mechanical stresses, and it's going to help ensure robust designs that can withstand real-world operating conditions. And so, yeah, in conclusion, ANSYS multiphysics solutions offer quantified benefits for achieving thermal reliability in electronic systems from accurate thermal models derived from detailed source data, which form the basis of reliability simulations, to advanced physics modeling capabilities, which is going to provide, which provided by ANSYS will allow engineers to gain critical insights into thermal performance, electron migration, and power management. And integrating IcePack results with Mechanical and Sherlock, you can comprehensively analyze the thermal impact on product longevity and reliability. Right. I think I just heard my VPN drop out. So I'm just going to.
While Rob connects to the VPN to run a demo for you, I would just like to say that besides providing a ANSYS solution by wild analysis, you could get various ranges of services from our expert engineers with 30 plus years of experience, who can assist you on your projects through consultation, tech support, bespoke training, etc. With wild analysis, you're not only receiving support from experts at ANSYS, but you'd also receive support from our dedicated and experienced engineers at Wild. So if you have any questions, please feel free to drop it in the message. And if there's anything that you would like to discuss, you can always reach out to us, and we can have one-to-one conversation regarding how we can improve your business structure, and also how our engineers can help you on your projects. So I'll hand this over to Rob now, who will do a demo for you.
Good, yeah, good timing. Yeah, so we're up and running now. So I think I showed some of you who was here last week, SI Wave, but we'll just do a quick tour again. This is the board that has already been imported. This is the workflow wizard. This is how, after you've imported, you will verify your stack up. So you can check all of the layers, make sure that the materials are right, the thicknesses are right, etc. You verify all the pad stacks, make sure your circuit elements have come in properly. You can do your power and ground net classification. We're going to go straight to the power drop analysis first. To do a thermal analysis, we need some electrical losses to act as sources for our thermal energy. Otherwise, if that didn't happen, we wouldn't have a problem. So what we're going to do is we're going to look at the power plane between this VRM and this integrated circuit here, this CPU. What we do is we apply a voltage source here, 1.2 volts, and if you want a current source, and we apply the current source to the CPU, we configure simulation, validate, and simulate. So what validate does is it checks that you've not made any big mistakes in your or obvious mistakes in your setup, to make sure that whatever's here is actually a number. And it will also go through your geometry to make sure that there isn't any anything that was going to make the mesh hard to generate, such as planes that are crossing over each other when they shouldn't. That's brilliant. So we've got no problems. I know that because I did it before. And then you end up here with power drop results. So I think we'll do this one, and you can we can have a look, and we can plot all of the currents, and these currents are going to cause resistive losses. So what we can do is we can plot an ice pack power map. And this is all of the power losses that have been calculated by the ice pack that is internal to the SI Wave tool. And after this, we have this power map. We can then go to simulation, ice pack, and then we can do a internal thermal simulation, including fluid flow. So we can look at the speed of the forced convection or natural convection. We can set all of that up. We can look at our components. So our components aren't solved in SI Wave, but we have the components within a library within SI Wave. So any component that you likely have imported through when you bring in your PCB file will be here, and it will have a power dissipation associated with it and a size associated with it from the library. That all adds up to the thermal sources that are within the PCB and are going to affect any of your cooling strategies. And once we've done that, we will click launch. I'm not going to do it live now because it will take some time, but you end up with an result something like this, if it will. There we go, and you end up with a temperature map, taking into account the flow that you've that you've applied to it. So if you are at the point where you haven't designed your flow capabilities in your design yet, but you have an idea of what it might be, this way you don't have to worry about exporting all of your PCB and applying all of your maps. You can do it within the PCB simulation solver itself. But all of these maps can be exported and applied to geometry in a 3D solver, like IcePack Classic, or the ANSYS Electronics desktop version of IcePack, where you could apply a bespoke casing with your own designed fans and then get more accurate representation of what your cooling strategy will do. But for a first approximation, it's very, very, I hope you can see it's very, very efficient and easy to do from within for an electronics engineer to do without needing all that much thermal knowledge. So it's very, very good for that. And I think we better move on to questions now.
Yeah, thanks, Rob, for doing the demo and also sort of giving our audiences the technical insight of using ANSYS products to tackle their thermal reliability. So we do have a few questions. So the first one is, can you model non-uniform material properties such as anisotropic thermal conductivity in ANSYS IcePack?
Yeah, definitely. When you apply your material properties, you've got a lot of power over what you can have. You can just put in just a block of thermal conductivity, or you can have an anisotropic thermal conductivity where you will define within the temperature within the material in, say, X direction, the thermal conductivity is this, in Y it's this, in Z it's this. Not only that, you could apply temperature conditions to that. So you could put a piecewise linear function in. So once it reaches a certain temperature within a steady state or transient, it will know what the temperature is, and then that will change. When you do a bidirectional simulation, it will change the resistivity based on that temperature and all this sort of stuff. So it's very, very yeah, it's very thermally and directionally aware.
All right, thank you for that. We have a second question. So what are the differences between steady state and transient thermal analysis in ANSYS? And when would you choose one over the other for assessing reliability?
So in steady state, you're assuming that the temperature distribution within the object of the system reaches a stable, unchanging state. And this means that any transient effects like heating or cooling over time are neglected. In steady state analysis, that's more suitable when the primary interest is understanding the long-term equilibrium of the system. And the advantage of that is it's faster compared to the transient. It's suitable for cases where temperature changes over time are relatively low or negligible. And it's useful for understanding distribution of temperatures under a consistent operating condition. But with transient analysis, if your system experiences rapid changes, like switching on and off, that's what you would use transient for, and it's essential then when you're looking at thermal fatigue or thermal stress during transient events. Like if you've got some sort of high power voltage source that's turning off and on and off and on, that's going to heat up the areas around it, like a cycle, rather than just it's going to reach a steady state condition. So that's when you would use that, and you can do both of those in ANSYS.
All right, thank you for that. We'll do one last question. Can ice pack be used to accurately model convectional heat transfer to intricate flow domain, including turbulence effect?
Yeah. So yeah, ANSYS can do turbulence modeling, no problem. It offers turbulence models such as the K epsilon model and K omega model, and it can also handle complex geometries. These are complex geometries are commonly found in electronic components, such as like the heat sinks or the enclosures. So if you can put enough mesh in there, there's a lot of mesh control to make sure that all of that can be modeled. And yeah, the boundary conditions and the sources and the heat sinks, they can all be there to sort that out. Yeah, with IcePack, it's cubic meshing, so you will have to put quite a lot of mesh in those small intricate areas, but it's definitely possible. And it's a thing you might have to look at to think, do I have the power for it? It might be something where you might need a HPC pack, but it's definitely a possible.
All right, thank you very much, Rob. And thank you everyone for joining today's thermal reliability webinar. If you have any questions or concerns, please do not hesitate to contact us. And we're going to have another webinar on mechanical reliability on the 23rd of August. So please do join us to understand how ANSYS simulation can help you maintain your mechanical reliability, highlighting the importance. And yeah, have a good day, and we look forward to seeing you in our next webinar. Thank you, everyone.